Imagine this simple moment. You drop a cup. It shatters instantly, and you know instinctively those fragments will never jump back together. Everyone understands that. But here is the strange part. The deeper you look into physics, the less obvious the reason becomes. Our world clearly moves in only one direction. Waves crash, we remember the past, and we hope for the future. Yet when physicists examine the fundamental laws of nature, they don't find a rule for this arrow of time. The equations governing atoms work just as well backward as they do forward. The laws of the universe themselves don't seem to care about the direction of time at all. So why does time only flow one way? We're still searching for the answer. To understand this better, imagine a simple system like a planet orbiting a star. Suppose we record a planet moving around the sun in an elliptical orbit. We film its motion as it travels through space, tracing its path over time. Now take that recording and play it backward. What happens? The planet still follows a perfectly valid orbit. It still moves along an ellipse. The speed changes exactly as expected according to the laws of gravitation. Every detail still follows the same physical rules. Nothing in the reversed motion violates the law of gravity. A physicist watching the backward video would not see anything impossible. The motion would look completely consistent with the equations that describe gravitational interaction. This tells us something remarkable. The law of gravitation is time-reversible. If you reverse the direction of time, the equations would still work perfectly. The same turns out to be true for many other laws of physics. The equations governing electricity and magnetism behave the same way. The basic rules describing nuclear interactions also appear to work in both time directions. In fact, most fundamental physical laws do not distinguish between past and future at all. In principle, if you could take every particle in the universe at a particular instant and suddenly reverse the direction of all their velocities, the entire system would begin retracing its previous history. Every motion would unwind itself step by step. The broken cup would reassemble. Waves would pull themselves back into the ocean. Smoke would gather back into the cigarette that produced it, at least according to the equations. And that creates the real mystery. If the laws allow processes to run equally well backward, then why does the real world only move in one direction? Why do we constantly observe things breaking apart, mixing together and spreading out, but never spontaneously reorganizing themselves? To answer that question, we have to look deeper into the behavior of atoms themselves. And when we do, we begin to uncover a surprising explanation hidden inside the chaotic motion of billions upon billions of tiny particles. To understand where the one-way direction of time comes from, we need to look much more closely at how matter actually behaves at the microscopic level. Atoms and molecules are constantly moving. Even in objects that appear perfectly still, the tiny particles inside are vibrating, colliding, and bouncing around with enormous complexity. What we see as calm and stable is actually a chaotic storm of motion taking place at an incredibly small scale. A good place to begin is again with something familiar, like the motion of planets. Earlier we saw that if you film a planet orbiting the sun and then run the movie backward, nothing about the motion looks impossible. The planet still follows a valid orbit, and the equations describing gravity work exactly the same way in reverse. The law of gravitation itself does not care about the direction of time. Now imagine a much more complicated system. Instead of just one planet orbiting a star, suppose we have thousands or even millions of particles moving around, interacting through gravity. According to the same physical laws, if we could suddenly reverse the velocity of every particle at a particular moment, each particle would retrace its path exactly. The entire system would unwind perfectly through all the events that happened earlier. This idea might sound strange, but mathematically it follows directly from the equations of motion. Forces depend on positions, not on whether time is moving forward or backward. If every velocity changes sign, every motion reverses itself step by step. In principle, a complicated process could run backward just as easily as forward. The same principle applies to other forces in nature. The laws governing electricity and magnetism also behave this way. If you film electric charges moving and interacting with magnetic fields, the equations describing their behavior remain valid even when time is reversed. Nuclear interactions, the forces holding atomic nuclei together, show the same symmetry. Even many forms of particle decay appear to obey rules that are essentially reversible in time. This creates a puzzle. The laws governing the motion of particles allow both directions of time equally well. Yet in the world around us, we constantly observe irreversible processes. Ice melts, but melted water does not spontaneously freeze into perfect ice sculptures. Perfume spreads through a room, but never gathers itself neatly back into the bottle. Broken objects stay broken. Where does this difference come from? At first glance, one might suspect that friction is responsible. Friction is something we encounter everywhere. When you push a heavy object across the floor, it eventually slows down and stops. If friction did not exist, the object might slide forever. And if you wait long enough, the object does not suddenly begin moving again and return to your hand. This makes friction look like a fundamentally irreversible process. But when we analyze friction carefully, we discover that it is not actually a basic force of nature. Friction appears because of the incredibly complicated interactions between the atoms of one surface and the atoms of another. When you slide a block across a table, the organized motion of the block gradually turns into tiny random vibrations of the atoms in both surfaces. In other words, the energy of motion becomes dispersed among countless microscopic motions that we perceive as heat. To see how this works more clearly, consider a simple experiment involving liquids. Imagine a container divided into two halves by a thin barrier. On one side there is clear water. On the other side there is water mixed with blue ink. At the beginning, the two liquids are completely separated. Now carefully remove the barrier. At first the blue water stays mostly on one side and the clear water stays on the other. But slowly the two begin to mix. The molecules of water and ink are constantly moving randomly, colliding and spreading through the container. Over time, the blue color gradually spreads everywhere. Eventually, the entire tank becomes a uniform light blue mixture. Now here is the important observation. Once the ink and water have mixed evenly, the mixture never spontaneously separates back into clear water on one side and blue ink on the other. If we filmed the mixing process and then played the movie backward, it would look extremely strange. The liquid would start uniformly blue, and then little by little the molecules would organize themselves, forming separate regions of pure ink and pure water again. That would appear completely unnatural. But suppose we zoom in and observe the molecules themselves during this process. We see billions upon billions of tiny particles moving randomly, colliding in every direction. Each individual collision follows the normal laws of physics. Two molecules approach each other, bounce off, and move away. If we reverse the motion of that single collision, the particles would still obey the same physical laws. Every microscopic interaction is reversible. Yet when we watch the entire system of billions of molecules, something different emerges. The mixing process moves steadily toward greater uniformity. The liquid becomes more evenly distributed over time. The key insight is that this direction is not forced by the laws of physics themselves. Instead, it comes from probability. There are enormously many ways for molecules to be mixed together randomly, but there are extremely few ways for them to remain neatly separated. If we allow random motion to continue long enough, the system will almost certainly move toward one of the many mixed arrangements rather than the extremely rare separated ones. Technically, it is not impossible for the molecules to reassemble themselves into two separate regions again. The laws of physics do not forbid it. But the probability of that happening is unimaginably small. For a system containing billions of molecules, the chance that random collisions will organize them back into perfect separation is so tiny that it would not occur even over the entire lifetime of the universe. And this statistical tendency toward more probable states is the first real clue to why time appears to move only in one direction. The statistical explanation becomes clearer when we think about just how many particles are involved in even the simplest physical systems. When we talk about a drop of ink mixing with water, we are not talking about a few dozen molecules moving around. We are talking about an unimaginable number of particles, billions upon billions, in fact, many trillions of trillions. Each of these molecules is constantly moving, colliding, and changing direction in random thermal motion. If we observe a single collision between two molecules, nothing about it looks irreversible. One molecule approaches another, they interact, and they bounce apart. If we recorded that collision and played it backward, the reversed motion would still follow the exact same physical laws. A physicist analyzing that collision frame by frame would see nothing impossible about the reversed version. Every detail would match the equations of motion. This means that at the microscopic level, the laws of physics remain perfectly symmetrical in time. But now, imagine watching the entire mixture of ink and water as a whole system. Instead of one collision, we see trillions of them. Gradually, the ink spreads until the entire container becomes a uniform shade of blue. If we played that movie backwards, something strange would appear. Ink molecules would gather on one side while clear water molecules would gather on the other. Eventually, the liquid would end up neatly separated again. When we watch such a reversed movie, we immediately recognize it as unrealistic. It looks like an enormous coincidence that millions of tiny motions somehow coordinate perfectly to create order. And that observation leads us to the heart of the explanation. The direction of time we observe is not imposed directly by the laws of physics. Instead, it arises from statistics, from the overwhelming difference between the number of disordered states and the number of ordered ones. Consider the number of ways molecules arrange themselves. In a mixed state, there are astronomically many arrangements that look roughly the same to us. Think of ink in water. It's easy for it to mix, but nearly impossible for random motion to bring those molecules back into a perfectly separated arrangement. Systems naturally drift toward the most common arrangements. This statistical tendency is what we call entropy, a measure of disorder. This leads to the second law of thermodynamics. In any large system, the overwhelmingly probable outcome is that entropy increases over time. This is why we see cups shatter, but never reassemble. This statistical drift toward disorder is what gives time its apparent direction. But if entropy always increases, how did the universe start in such an ordered state? To find out, we must look at the history of the entire universe. Entropy naturally increases, moving systems from order to disorder. But if everything becomes less organized over time, how did the universe begin in such a highly ordered state? Think of a tank with ink and water. If it's only partially mixed, we infer it was once perfectly separated. This isn't direct observation. It's understanding the direction of entropy. This reasoning allows scientists, from geologists to astronomers, to reconstruct the past. It suggests the early universe was far more organized than it is today. Some suggest our ordered world is just a rare fluctuation in a chaotic void. But if that were true, the rest of the universe should look chaotic, and ordered structures would be incredibly rare. Understanding entropy doesn't just tell us where we're going. It gives us a profound clue about where we came from. However, when astronomers look out into space, they observe something very different. Everywhere we look, we find the same kinds of structures. Stars forming inside galaxies, planets orbiting those stars, and large-scale patterns repeating throughout the cosmos. This consistency indicates that the universe as a whole began in a highly organized state. Physicists often describe this early condition as a low-entropy state, a state of unusually high organization. As time passed, entropy gradually increased, energy spread out, and the level of disorder continued to grow. This gradual increase in entropy is what gives time its arrow, the sense that events move from past to future. Broken cups and fading stars all reflect this same underlying trend, the movement from order toward disorder. Yet even with this explanation, one profound mystery remains. Why did the universe begin in such a highly ordered state? Understanding that origin remains one of the deepest unsolved problems in modern physics. Because the ratchet allows motion in only one direction, it might seem that these random pushes would gradually rotate the wheel in that allowed direction. Every time the vanes receive a push forward, the wheel would click ahead slightly. Whenever a push tries to move it backward, the pawl would block the motion. Over time, the wheel might keep turning forward indefinitely. At first glance, this looks like a clever machine that converts random molecular motion into useful mechanical work. If it worked, the device could produce motion endlessly, without any external energy input. In other words, it would create perpetual motion powered by the thermal motion of molecules. However, when physicists analyze the details more carefully, they discover that the device cannot actually work that way. As the system operates, the part of the device containing the ratchet and pawl gradually warms up. The energy generated by friction spreads into the surrounding metal. Once that region becomes warmer, the pawl itself begins to experience stronger molecular vibrations. Eventually, these vibrations become large enough that the pawl occasionally lifts slightly away from the ratchet teeth. To understand this intuitively, imagine using dry towels in a rainstorm. Once the towels are as wet as you are, you can't get any drier. This is the essence of equilibrium. Energy in the universe is conserved, but its availability decreases as entropy increases. Differences disappear, and systems move toward equilibrium. This is the second law of thermodynamics. The arrow of time that we experience, the sense that events unfold in a particular direction, emerges from this gradual loss of usable energy and the steady increase of entropy throughout the universe. At this point, we can finally bring everything together and answer the original question. Why do broken cups never reassemble? Why does ink mix with water but never separate again? Why does time appear to move only forward even though the fundamental laws of physics seem perfectly happy to run in reverse? The surprising answer is that the laws themselves do not forbid reversal. Every individual interaction between particles, every collision between molecules, every force between atoms works just as well backward as forward. If we could reverse every velocity in the universe at one instant, the equations of physics say the entire system would retrace its history perfectly.